All right, so it's week 3, day 3, and we're still talking about vector fields, line integrals, and work. It's the same topic as yesterday. Chapter 18 is released for Monday, all right? So if you want to take a look at that over the weekend, don't worry about that for tomorrow's test, okay? That's Green's theorem. We're going to be talking about the 3 great theorems, actually 4 great theorems of multivariate calculus next week. That's the capstone of the course. Green's theorem for work, Green's theorem for flux in the plane, Stokes' theorem for work in space, and Gauss's theorem or the divergence theorem for flux in space. We'll talk about that next week. So we started talking about work and line integrals yesterday. Let's take a look at another one. Okay, here we go. Here's an example. Alrighty. So I'm back to squid, and I got geometry on here. Let's see if this works better. I didn't like the geometry on that thing yesterday. You know, the thing that draws straight lines for me, right? Because I can't draw. Okay. All right, so remember what we said. What we're trying to do is we're trying to find the line integral over some curve C, a path in space. But right now we're in the plane, so make it easy. We're not going to go crazy into space until next week. And what we want is f dot dr, where f is your vector field, or it's the projection of the force vector along the curve in the direction of the velocity vector. So if you have a parameterized curve, right, r of t, as if t equals 0, you're here, t equals 1, you're over here. As t increases from 0 to 1, the r vector, the radius vector, right, the position vector, points to different positions on your curve. So it describes that, right? But the velocity vector along the curve, what does that look like? Remember yesterday we were calculating the velocity vector? I don't know if I made that clear. Why? Why am I calculating the velocity vector? Because work is force dot product distance, right? Or displacement. The force vector dot product of displacement vector. But the displacement vector is a piece of arc length along the curve. So I need to figure out what that is, what direction that is. Isn't that going to be tangential to the curve? And isn't the velocity vector tangential to the curve? So we're actually trying to do this. This is really what we're doing. So f dot tangent vector d little s. What does that mean? It's a dot product of the tangent vector, the unit vector, see the hat? The unit vector tangential to your path, okay? So that I can project the force in that location, I can project the force vector in that direction, right? Because remember what the dot product does, it gives you that piece of the force in the direction that you're going. Times ds is the length of the little piece of curve. Remember, there's a Riemann statement, right? We're just taking little pieces of the curve, figuring out the work done along all these little pieces, and then adding them up with the integral, right? Okay, so it's tangential to the curve. So what does that have to do with r? Well, the velocity vector is tangential to the curve. So this is equivalent to saying okay, you can write it this way. How about this? This is equivalent. Wake up, what are you going to sleep for? Okay, let's say your vector field is Mn, right? It has a horizontal and vertical component. Horizontally, I'm going to call that M. It could be a function in, x squared plus 2. And then it could be xy, whatever it is, right? And N is your vertical component of the vector field. Remember, we graphed a few vector fields yesterday. Excuse me. Dot xy, dx, dy. This is the same thing. This is vector-wise. Right, geometrically speaking, the angle in between and the cosine of the angle, all that stuff. And this is component-wise. How do you do a dot product with two vectors that have a delta x and a delta y component? What's a dot product? It's going to be m dx plus n dy. So you could do it component-wise too. You could say, okay, I'm really just integrating this. That's what I'm integrating. But sometimes it's hard to do because you got a dy and you got a dx and you got all kinds of mixed variables and so forth and so on. So that's why we parameterize the curve. We try to rewrite this whole thing in terms of one variable. Since we're going along a curve, there's only 1 degree of freedom. So we should be able to write this in terms of one variable. There's too many variables running around. So I'm going to show you how to do it this way and this way. Sometimes you can do it this way, sometimes you can't, and you want to do it that way. You can usually get away with it this way. So I'm going to practice that up a little bit more today. I don't know if that was, how was that yesterday? Was that weird? Was it weird? Yeah. You realize what's going on. It's like you have a, okay, here, you're on a roller coaster, but it's a baby roller coaster. It's on the XY plane. It doesn't go up, it doesn't go down, it just goes across the plane because you're 2 years old. You can't do that. There's such a thing, baby roller coasters, right? I'm not making this up. And there's a huge vector field, a huge wind vector field, like a hurricane is coming or something. And what we're measuring is the work that the field does to push that roller coaster along the track. But the track is your path. So how much work does the wind do to push the kid along the track? Say it's actually strong enough to push the kid along the track. And that work is how much energy is expended, right? Then we talk about a work problem somewhere along the line. We got Newton meters, something little Newton meters, like 5 million, right? And isn't that joules? Newton meters is a unit of energy. So how much energy is expended, right? So vice versa, how much energy does the vector field expend on moving this thing along the track? Or if you're on the track and you're moving against the vector field, how much work do you have to do to stay on the track and do what you want to do, go along the track against the wind, right? That's what we're calculating, okay? So, all right, so here's an example. Let's say, all right, so let's say I ask you this. All right, let's go to Sage. Here we go. Sage, where are you? Sage. Do you have a Sage open? There you go. Okay, Sage. Okay, so here's my first example for today. All right, number 1. How are we going to write this? Let's see. Evaluate the line integral of m dx plus n dy is, in fact, what do I want to make it? Y dx, I'm going to write it Sage-wise, y times dx plus, what is it? Let's see. Go away. Okay. Keyboard is in my way. Go away. Sorry, keyboard's messing me up. The old keyboard. All right. X squared dy. So how do you evaluate this? X squared times dy. All righty. Along the curve, let's say C is, what is it? What is C? What do I want for C? Y equals 4x minus x squared. Okay, so y equals 4x minus x squared. Minus, where's the minus? Okay, is that what I want? Okay. Now I have to tell you where you're going. From the point 0, 0, no, from the point 4, 0 to the point 1, 3. All right, so I want to travel along that curve between those 2 points. By the way, are those 2 points on the curve? If I plug in 1 for x, do I get 3? Right? If I plug in 4 for x, 16 minus 16, do I get 0? These are endpoints for my path. And you're going along the path, right? Now, by the way, what shape is this? If you graph y equals 4x minus x squared, it looks like a what? Yeah. A parabola kind. Open up, open down, open left, open right, open and down, right? So this, okay. I think it has an x-intercept of 0 and an x-intercept of 4. So it's like it's going through 0, 0, 4, 0, and it's like this, right? And I'm going from 4, 0 to 1, 3. I'm doing this is the path right here. That piece of the parabola, right? So how do you calculate this work? Do you have to parameterize the region? Not always. Because I'm trying to do y dx, I'm trying to integrate y dx plus x squared dy. But can I rewrite this all in terms of x, let's say? Could you? What's y in terms of x? It's staring you in the face. What is it? The parabola, right? 4x minus x squared. Okay. So I could replace y with 4x minus x squared. So that's in terms of x dx. Now I can integrate that. That's good. That's what I want. Then x squared dy, but I can't integrate that. I need a dx here. Well, what is dx? Sorry, what is dy? The differential of y. What's dy dx? Ordinary derivative. Not partial. What's dy dx? What's the slope of the tangent line along that curve? Elementary calculus. It's going to be what? 4 minus 2x. So dy dx is 4 minus 2x. dy alone is bring up the dx. 4 minus 2x dx. So I could replace this with 4 minus x dx. Okay. So, how would I write that? All right, so let's just do it. Here we go. Ready? So, show the integral. Remember, there's a line integral. It's just one integral. It's not a double integral with an integral of an integral, any of that. It's not a triple integral. That's coming next week. Okay, of what? Well, we said, I want in place of y, I'm going to write 4x minus x squared. Okay, so let's write that. So it's going to be 4 times x. You know, there's a Bluetooth mouse in here somewhere. I should probably set that up so it's easy to cut and paste, but I gotta play around with that. Okay, x, I already wrote this. This is bugging me, x squared. Okay, that times dx, right? Plus, and they're both gonna be times dx. I'm gonna factor out the dx. So plus what? Plus your dy times x squared. But dy was 4 minus 2x, okay. So plus, plus the quantity 4 minus 2 times x times the x squared. Because it was x squared times the dy, and the dy is 4 minus 2x dx. And so I'm integrating all of that stuff with respect to x. That's your dx right there. But what are the limits of integration? How does x vary? Because I'm doing this with respect to dx, right? So tell me how x is varying along the curve. From what to what? Look at it. X starts at 4 and it goes to, yeah, that's it. And unless I messed up a parentheses or something, I'm good. Where'd it go? Yep. 69 halves, or what would that be? 34.5? 34.5, I don't know, Newton meters, whatever the units are. Okay, so if the force is in newtons, if the force vector, if the vector field F is measured in newtons, the magnitude of the vectors is measured in newtons, and the dr, the velocity vector along the curve is measured in meters, or the r is measured in meters, you're getting Newton meters, 69 halves of Newton meter. So what we did yesterday was we had some examples where it was hard to do what we just did, replace the y with something, replace the dy with something. So I didn't even bother. I just went to a parameterized version of the problem. You know, just out of curiosity, could we do this parametrically, this one? Let's see about this. What do we got? We've got a force vector. Where did it go? We have a force field, or vector field, where m is y, and n is x squared. Isn't it? Where did I get that from? I'm saying that m dx plus n dy is y dx plus x squared dy. So in other words, m, the horizontal component of the vector field is y, and n, the vertical component of the vector field, is x squared. So is there a way to do this parametrically like yesterday and get the same thing? Let's see. So there's your force vector. Now your position vector, parametrically speaking, is what? Well, we're going along this thing. What the heck was it? 4x minus x squared. Is there a way to parameterize that as a position vector x of t, y of t? Like if it was, like we did this yesterday, what if we said, oh, I want the quarter circle, center to the origin of radius 1, from 0 to pi over 2. We said, oh yes, cosine of t for x and sine of t for y, because that's r, that's x equals r cosine theta, x equals y equals r sine theta, right? We can parameterize the circle real easy. So we parameterize the parabola. Would this work? Let's see. If you let x of t, I'm just playing with this, whoops. If you let x of t be t, then y of t would be 4t minus t squared, wouldn't it? I think parabolas are pretty easy to parameterize. I mean, you can do it a lot of different ways. But if you let the x be the t, so x of t is t, then the y of t is just plug in t wherever you see x. That's all I'm saying, let x equal t. What's your velocity vector now? 1 minus how much? 4 minus 2t. Okay. So how do you form f dot dr? What do you do to get f dot dr? This is how we did it yesterday. And then we integrate that with respect to t. I want to make everything in terms of t, parameter t. Again, one variable, one degree of freedom, one variable. When we do this in three space, it's going to be two variables, 2 degrees of freedom, because we're going along the surface. But then we're not going to be doing line integrals, we're going to be doing surface integrals. That's next week. So what's the dot product? T times, I want the dot product, I'm sorry, I'm doing the wrong thing. I want the dot product of f and dr. This is dr, the derivative of r, right? So I want f dot dr. Here's dr, the v. But f is in terms of y. Well, what did we say? Wherever you see y, you're going to put this. This is y. This is x of t. This is y of t. So wherever you see y, you're going to put this, 4t minus t squared. Wherever you see x, you're going to put t. Because we redefined x equals t and y equals 4t minus 2 minus t squared, right? So that's how you do the dot product of f dot dr in terms of just t. Now, you could do it this way. You say, okay, y times 1 is y plus x squared times stuff, and then go later on just plug back in what x and y are, you know. But all right, let's write that. Let's say, okay, this is really what we said y is 4t minus t squared, and this is really x squared where x is t, so t squared. So take the top thing I just wrote, dot product of velocity vector. That's what I'm calling dr. So you get 1 times, how do you do a dot product? We just did it. 1 times 4t minus t squared plus, where's 4 minus 2t times t squared, right? Okay. So let's write that out. So it's 1 times 4t minus t squared, so it's 4t minus t squared, plus t squared times 4 minus 2t. How about we distribute the t squared? 4t squared minus 2t cubed. And you can simplify this a little bit. Isn't that just 3t squared? So I have a negative 2t cubed plus 3t squared plus 4t. Now, that's your differential for work. That's your dw, along a little strip of your path, right? So how do I add up all the work that I'm doing along the entire path? Integrate, right? Because that's what an integral is. It's a humongous sum of all these little pieces. Okay. So if I integrate this from what to what? From t equals what to, I'm integrating this to t, right? So I want to integrate from t equals what to what? Well, we were integrating for x was going from 4 to 1, was it? What the heck was it? How do we write that? Look at the integral. We were integrating as x goes from 4 to 1. So t goes from what? So So t is going from what to what? Nobody knows? Also 4 to 1. Why? Because then we make x equal to t. So whatever x is doing, t is doing also. Yes? This is not always the case, right? If you're parameterizing the circular path, you're doing 0 to pi over 2. It's not the same as what you would do in terms of x and y, right? It's different. Okay, so let's integrate this thing. So I'm integrating, what's it? Negative 2t cubed. So the integral over the path C, that parabola, of f force vector field dot dr, or the force along the curve, is the integral from 4 to 1 of negative 2t cubed, was it plus 3t squared plus 4t, right? Plus 3t squared plus 4t. I'm just writing it in standard form with respect to t. All right, so how do you evaluate this mess? It's just a single variable integral, right? There's elementary calculus now. So what do you get? Negative t, whoops. Hang on. Negative 2 what? T to, what did I just do? Negative 2 t to the 4th over 4, right? Plus 3t cubed over 3. We'll reduce it later because I got to reduce it to 4ths anyway. Plus 4t squared over 2. Yeah, 2t squared, right? Evaluated from 4 to 1. So let's do that. Plug in 4. Well, I should probably simplify this a little bit. Isn't that negative t to the t over 2, negative t to the 4th over 2, plus t cubed, plus 2t squared from 4 to 1? I'm running out of space, sorry. Is, okay, let's plug in the 1. So 1 to the 4th is 1, negative 1/2. Plus 1 cubed is 1. Plus 2 times 1 squared is, that's squared, is 2. Quantity minus what you get when you plug in 4. What's 4 to the 4th? Wow, this is huge. Did we do something wrong? We're supposed to get 69 halves. This is sort of huge. All right, what is 4 to the 4th? 256? Ooh. So negative 256 over 2 plus 4 cubed is what? 64. Plus 2 times 4 squared is 2 times 16 is 32. And miraculously, you get 69 halves, don't you? Because that's what we got a minute ago. So it's got to be right. Is that what we get? Let's see. So we got 1 plus 2 is 3 minus 1 is 1.5. 2.5. So 5 halves. That's 5 halves. And then this is what? Negative 128. Negative 28. 128 plus 96. What is that? 224.
It's not that.
It's not that. 224 and wait, this was negative 128. Wait, this is negative 128 plus 96. Negative 128 plus 96 is 32, right?
Yeah.
32. And that was negative 32. We're subtracting, so it's positive 32 plus 2.5 is 34.5. Ye of little faith. Did. Yeah, it is 69 halves. Isn't that 34.5? Yeah, it works. Okay. So you could do it parametrically, but wait, look at that. What a mess. Or you could do it, component-wise. Did we do it component-wise? That's how we did it on stage. And one or the other way is easier usually. This is usually hard. This turned out to be easy in this example. So this is the way to go for this one. So you try to set it up both ways and make sure you do it the easy way. If you can do it component-wise, boom, you're done. Just do this. If you can't do it component-wise, do it parametrically. Define the curve, the path of your, where you're doing the work as a parametric function in terms of t, as a position vector with an x component and a y component. X is a function of t and y is a function of t. And that's what we did. Okay, good, perfect. All right, so does that make yesterday a little bit more understandable? Because I'm doing the exact same thing I did yesterday, but this new way. This is new. We didn't do it that way. Yesterday, I gave you an example where doing it parametrically was really hard. As I'm doing it that other way, component-wise, was really hard. And doing it parametrically was easier. In this case, doing it parametrically was a pain. But you still get the same answer. It's the same thing. It ends up being the same thing. Because with the way we did it over here, f.dr, that's dealing with the geometric interpretation of the dot product using the angle in between, all that kind of stuff. But the way we did it over here was the component definition of the dot product. You take delta x times delta x plus delta y times delta y. It's actually a little bit of both in this. There's a little bit of both in this. All right, so questions? How are we doing? That's if your path is a circular path, but we had a parabolic path where we're going from 4, 0 to 3, 1, or is it 1, 3, whatever. Was it 3, 1 or 1, 3? I forget. It was 1, 3 because it went from 4 to 1 in x, right? So it was 4, 0 to 1, 3 along the parabola. So it was easy to parameterize that, but was it easy to do it parametrically? It's a pain. I mean, it's not hard, it's just tedious. Is it hard? No. Is it a pain? Yes. You got to pick the way that's going to be easier for you to do, right? Unless you like to do it the hard way. That's fine with me if you want to do it that way. All right, so hang on. So let's play around with it slightly more, and then we'll get to the review. Take a look at this example. How am I going to do this one? Okay, here's another example. Let's say, all right, let's do this in squid. Squid, come back. Okay, so say you want a line integral of FDR where C is a smooth curve from 0. How am I going to do this? Hang on. Wait. I'm trying to find the. Here it is. Hang on. Okay, so we want to figure out the line integral over the path C of f.dr. In other words, the work done by that vector field, where C is the path. How do I want to make the path? Is a smooth path, which is. Oh, here's C. I'm going to draw it. Okay, here comes the geometry. Hang on. Okay, how do I do geometry on here? Okay. Oh, that's skinny. Okay. What else do I want? Let's make a circle. Okay, so it's a circle centered at 1, 0 of radius 1. Can I draw that? No, of course not. Pretend that's a circle. Dang it. Pretend that's a circle of radius 1 centered at 1, 0. Okay, where's my pen? Where did my pen go? Give me a pen. All right, so this is the point 1, 0. Here's your x-axis, here's your origin, here's your y-axis over here. Okay, and I want to go from the point, let's see, 0, 0 to 2, 0. So I'm going along the curve from 0, 0 to 2, 0. All right, so here's the curve. I'm starting here. I'm moving along the upper half of the circle. I'm stopping here. Okay? So I'm doing a circular path, but this one is not centered at the origin, okay? A little bit different. And my force vector, my vector field is it's this. Let's see, what do we want? It's going to be, where is it? Y cubed plus 1, comma, 3xy squared plus 1. Whoops, I did it wrong. 3xy squared plus 1. Yes. Okay? All right. So how are you going to do that? If this is mn and this is dx dy, can you just do m dx plus n dy? Can you do it component-wise? So m would be y cubed. Wait, hang on. So let f dot dr equal m, which is y cubed plus 1 quantity dx, plus n, which is 3xy squared plus 1 dy. Is there a way to get rid of the y's like we did last time? Can we do this all in terms of x? Why is this not the same as before? Because we don't have y like in parabola. Y is a function of x. We can't just plug in y as a function of x here. We can't just differentiate and get dy, right? And then do everything, right? Can we? Or can we? What's the equation of that circle? Do you know how you write the equation of a circle? X minus h squared plus y minus k squared equals r squared, right? Could we do that? Maybe we can get away with this. All right, let's see. So x minus h would be x minus 1 plus y minus k would be y minus 0. So we squared y equals r squared is 1. The radius is 1, right? So, whoops, y squared. So could we replace all the y's in terms of x's? Well, look, I need y squared here. Y squared is simply 1 minus x, 1 minus the quantity x minus 1 squared. Well, that's a nice easy substitution. If y squared is 1 minus that, then 2y dy is going to be 2x minus 1 to the 1. You could replace that, dx. Y cubed, though. How are you going to get y cubed? That's going to be a mess. You could do it, couldn't you? You could say, okay, if y squared is 1 minus quantity x minus 1 squared, then y is the square root of that. And y cubed is cube that, and put that here. Good, but are you going to be able to integrate that with respect to x? Not really. Oh, well. So that's a problem. So, can we parameterize this? Can we do this in terms of sines and cosines and whatnot? What if we replaced all the x's up here? Right? This is c right here. C is x minus 1 squared plus y squared plus 1 as x goes from 0 to 2. Right? That's my c. That's my path. And my force vector, my vector field is working against me walking along this path. Right? So how much work is being done? That's what we're trying to figure out. All right. Well, remember how do you convert to polar coordinates? X equals r cosine theta, but r is 1. So I could just write cosine t here and sine t here and solve for can we do this? Wait, let me think about this. X minus 1 squared. Okay. See, this is a pain, isn't it? The point is, this is a pain. I'm going to show you a real easy way. Hang on. This is the point to the pain. It's a point to the, there's no pain, no gain, okay? It is painful, right? Okay, hang on. Let's see if we can figure this out. If x minus 1 squared plus y squared is 1, can we rewrite that in terms of sines and cosines? All right, well, let's see. Cosine of t minus 1 squared plus sine squared of t is 1. So if you square that out, you get cosine squared t minus 2 cosine t plus 1 plus sine squared t is 1. Does that do anything for us? Well, what's sine squared of an angle plus cosine squared of the same angle? 1. So, and then there's another one here. So then we got really 2 minus 2 cosine of t is 1. Does that help? Is what 0? Not yet. I was thinking that, yeah. I was thinking, why don't we just subtract the 1 from the 1 and got a 0 here? But I combined the 1 with the 1 and I got a 2 here. So what does that do for me? It's hard to parameterize this curve, isn't it? Let me think. Is there a way to make this easy? This one's a pain. Yeah. But that just gives me one value of t. I don't want that. I want x as a function of t and y as a function of t, such that if I plug in different values of t, I go through that semicircle. I traverse the semicircle. This is not doing it. Wait, all right, let's think about this. X minus 1 squared plus y squared is 1. Before we plug in r cosine theta, r sine theta, what if we just FOIL this out? X squared minus 2x plus 1 plus y squared is 1. So y squared is, let's see, 2x minus x squared. So y is, see, this is almost a parabola, right? If it was just said y equals 2, I could have parametrized this like last time. Make x equal to t and make y equal to 2t minus x squared. But since it's not, I'm square rooting that. How do you parameterize that? Wait, let's look at the diagram again. What part? Oh yeah, positive negative. Yeah. I was just looking at the principal root. Yeah, it could be positive negative. I want to write this in terms of what is x in terms of theta, and what is y in terms of theta. Think about this. You got a point here. Let's say it's x and y. No, not that. Can you calculate x and y? Whoops. In terms of r and theta. The problem is that r is not a constant. That r is changing, right? So as this point goes from here across the semicircle to here, r is changing. So this is hard. X squared plus y squared is r squared. X is the cosine. Oh, okay. X is the cosine of theta times r, right? But, oh, okay, it's easy. Oh, look. Think of the circle. This circle is centered at 1, 0 and has a radius of 1. So the diameter goes from 0 to 2, right? What if we just shift it over a little bit? What if we made the center 0, 0? Right? If we make the center 0, 0, the circle is here, it's of radius 1, then we can parameterize it as x of t is cosine t and y of t is sine of t, right? The only difference is that the x values are really 1 unit farther apart from that. I'm shifting all the x's over 1 unit. So isn't x of t 1 plus cosine t? How about that? X of t is 1 plus cosine t, and y of t didn't change. I'm just shifting along the x, right? Ah, there's the parameterization. Perfect. Okay, so how did we start this? Okay, so I want to parameterize this mess. All right, so let's start over. So I want such that f is, what did we say it was now? Y cubed plus 1, comma, 3xy squared plus 1. Good. Okay, and r of t is 1 plus cosine of t, sine of t. Right, so remember, we tried to do this component-wise, it was just a mess. Now let's do it parametrically, yeah. Well, let's run with this for a minute, see what happens. So remember what we did? We want the dr, which is really the velocity vector, tangentially, right? So isn't that v of t? Stop it. So what's v of t going to be? What's x prime?
Negative sine t.
The x of t is negative sine t, and the y of t? Cosine t. Okay, so negative sine t and cosine of t. So how do you form f dot dr? It's a dot product of f, there it is, and dr, there it is, it's a v, except you want to write y as sine and x as 1 plus cosine. Okay, this is doable, but it's a humongous mess. All right, so guess what? I'm going to let Sage do this part for me. But this is parameterized correctly. You should be able to get an answer out of this, right? Okay, hang on. So here we go. Let's do this one. So number 2. Oopsie. So I'm going to let the vector field be this. Let f equal a vector. I mean, you could do it by hand, but it's getting to be a mess, so let's Sage do the rest, okay? But we got the setup, that's the point, okay? So it's a vector made up of a horizontal component. Now, instead of writing y cubed plus 1, what am I going to write? Instead of writing y cubed plus 1, I'm going to write cosine cubed t of plus 1, right? Okay. And likewise, instead of writing 3xy squared plus 1, I'm going to write 3. Wait, did you say cosine for y? It's this. This is y. This is dy. So this, you said sine, right? Did you say sine? You said right. So this is sine cubed plus 1, and this is 3 times 1 plus cosine times sine squared plus 1. Okay. That's exactly what I got. Okay, good, perfect. All right, so let's do that. Okay, here we go. So the horizontal component is sine of t cubed plus 1. Okay, so quantity, sine of t cubed plus 1. That's the x component. That's your m. Here's your n. 3xy squared plus 1 turns into, I wrote it down somewhere, 3 times 1 minus cosine t. Okay, 3 times quantity 1 minus cosine of t. Okay. Times y squared, which would be sine t squared, and then there's a plus 1. So times, what did I want? Sine of t squared. So quantity sine of t squared, and we're adding 1 to that. We're adding,
1 minus cos.
what about it?
I thought it was 1 plus cosine.
Where did I get 1 minus from? It is 1 plus. Isn't it? Hang on. It is 1 plus, right? Why do I, my notes are wrong. Okay, you're right. Okay, so it's y, so, okay, so this, let's get this straight. This is y cubed plus 1. This is 3x, we said plus, right? 3x times y squared, and then the y squared, there's a plus 1 after that. And what happened? Oh, I lost my square bracket. Dang it. I don't want the square bracket there. Okay, so those are the two components, right? Let me just show it, make sure I didn't mess up something. Capital F for vector field, by the way. And there's t's and stuff, so I better var t, right? Var t. Well, did I enter that correctly? Okay, so there's the mess, okay? So this is y cubed plus 1. This is 3x y squared plus 1. Perfect. Okay. In terms of t. I want to dot product that with the velocity vector, right? But remember, what was the position vector? We got to put that in. So R is a vector made up of components, and it was 1 plus cosine t, right? 1 plus cosine of t, and then sine of t. Okay, there you go, good. And just for fun, let's just show that, make sure everything's entered correctly. No big surprises later with 50,000 errors. That's a parameterized position vector, x of t, y of t. There it is. Okay. Now, what do I do with the r of t? Take derivative. I want the dr, which is really the velocity vector dt. Okay, so I'm going to say v equals the, guess what? Huh? Diff, right? Diff of the position vector with respect to t. Where's the t? And let's show that, see what it looks like. But of course, you can predict this very easily. V of t or dr is v of t dt, right? So and there you go. Okay, so what we want to do is integrate f as a f, the vector field f in terms of t, dot product this v in terms of t. And we're integrating with respect to t, from t going from what to what? What are the limits of integration, by the way? Well, wait, let's go back to the diagram. Where did it go? How do I get from here to here using what we said, that x is 1 plus cosine t and y is sine t? If you start with 0 for t, is that okay? You start with 0 for t? How do you get 0, 0 from 1 plus cosine t? That's when cosine t is -1, so it's negative pi, right? The cosine of an angle is -1 when the angle is negative pi. Up to Here, when is cosine t plus 1 equal to 2? What's cosine t plus 1 equal to 2? When cosine t is 1, when is cosine t equal to 1? At 0. So it's negative pi to 0? Is that true? Well, now notice also the y values have to start at 0 and end at 0. I want the x values to start at 0 and go to 2. So if I plug in pi, or negative pi, either way, I'm there, and I plug in 0. So I'm going to try this, negative pi to 0. Okay. Negative pi to 0. All right, okay. So, all right, so that's what we're going to do. Here we go. So let's do the dot product. Let's call that, I'm going to just call it FDR, not the president, is F in terms of T, dot product, the V. And let's see what that is. That's F dot dr. I should say F, how about dot dr? How about that? So that's the dot product. And I'm going to integrate that with respect to T and make it a definite integral from negative pi to 0. Okay. Which is a pain by hand, but hey, we got a computer algebra system here. Let's see if we can do it. So show, what did I get for this answer? Right? Yes. Okay. Show the integral of that thing we called FDR with respect to T from negative pi to 0. And you get 2 Newton meters, whatever. Now, that was a royal pain, was it not? Enter the fundamental theorem of line integrals. Makes nice stuff for these problems. If you have a gradient field, what does that mean? If your vector field you're talking about, big F, is conservative and well-behaved, defined everywhere, differentiable everywhere, partials exist everywhere, all that stuff, right? You don't have to do any of this stuff. You just have to take the potential function and plug in the endpoint that you're going to and the starting point where you started and subtract. What? What are you talking about? Really? What's the potential function for this thing? Well, let's go back to this. Can we get a potential function for this thing? All right, so look, this is what I'm saying. Do you know the fundamental theorem of just plain old elementary, good old elementary calculus, right? It says that the definite integral from a to b of f prime of t dt is f of b minus f of a, as long as everybody's continuous and differentiable and the antiderivative exists and everything. So usually we say, if this is x, this is x squared over 2. If f prime is x, f is x squared over 2, because the antiderivative's derivative is what you started with. The derivative of this is what you started with, right? But the point is this: if you have nice, behaved, smooth, continuous curves, differentiable curves, right? Nothing weird going on. The area under the curve, bounded by the curve in the x-axis, whatever it is, has only to do with the endpoints where you start and where you end up. That's it, right? Okay. That's what the fundamental theorem of line integrals says, sort of also. Let's see. I'm going to write this. The line integral over some path C of grad f, gradient f, del f, remember the gradient? Dot dr is nothing more than the potential function evaluated at P1 minus the potential function evaluated at P0. Where P0 is where your path starts, and P1 is where your path ends. Isn't that just a lot easier? So if the F we just did, that big, huge, humongous mess, if it turns out to be a gradient field, a conservative function, a conservative vector field, then all we got to do is figure out the potential function and plug in the point, what was it, 2, 0 we stopped at, and 0, 0 we started at. All in terms of x and y. F of P1 minus F of P0, where P0 is the point you're starting on in your curve, your seat, your path, and P1 is where you're ending up. So this would be the 0, 0, then go along the semicircle to 2, 0. All you got to do is plug in that into your potential function, plug in that into your potential function, subtract the 2, walk away, you're done. That's it. But you got to get the potential function. So if this is a gradient field, there is a potential function because the gradient of the potential function is the vector field. So is that what's going on here? Let's see. What if I go back to the beginning and talk about F, where M was, what was M? Y cubed plus 1, right? And N was 3xy squared plus 1? So how do you know if it's a gradient field? How do you test that it's conservative? Right, take the M, which is really little f sub x, differentiate it with the first partial with respect to y, and see if it matches if you do that to n, but first partial with respect to x. Why? Because this is supposed to be f sub x. If you now take this y, the mixed partial with y, it's f of x y, f sub x y. But this is supposed to be little f, the potential function sub y. Now if you do it again, the mixed partial, with respect to x, you get f of yx. But what did we say about the mixed partials of a function sub xy and sub yx? They're the same. That's only true if it's a conservative vector field. We're only dealing with that. So, is this a conservative vector field? What is the derivative of y cubed plus 1 with respect to y? The first partial with respect to y, what? 3y squared. What's the first partial of 3xy squared plus 1 with respect to x? 3y squared. Aha! So it is a conservative field. So if this big F is a conservative field, you must be able to find little f, the function, the potential function that we're talking about. So how do you do that? If fx is y cubed plus 1, how do you get f? Right? If m is the first partial of the potential function with respect to x, then f is the antiderivative with respect to x, right? So what would I write? xy cubed plus x plus a constant, right? What, right? But wait, this constant has to be a function of y. Remember we talked about this? Because in this case, how do you check your work? The first partial of f with respect to x is differentiate this thing with respect to x, keeping y a constant, right? So the derivative of this with respect to x is y cubed. The derivative of this with respect to x is 1. The derivative of this has got to be 0, but it doesn't have to be. It doesn't have to be 0. It doesn't have to be a real constant, a real number. It could be some function in y because we're calling y constant. So what if this was like y cubed and you differentiate with respect to x? It would give you 0. I don't know what the heck it is. How do you find out? Right, now take this thing, which is my guess for the potential function. Take its first partial with respect to y, and match it to this, the n, which is supposed to be the first partial with respect to y. And that'll give you a hint as to what g is, if it exists at all. It might even be 0, who knows? Okay, so let's find out. So what is f sub y if that's my f, my little f? Differentiate that last line with respect to y, first partial with respect to y. What do you get? 3xy squared. Does that look familiar? Okay, so 3xy squared plus 1 plus g prime, whatever it is, with respect to x. So we got the 3xy squared. We got the 1. Well, guess what? G prime is 0. There's nothing here to match up to g prime. So if g prime is 0, is it a function of y? Because I'm differentiating this with respect to x, and I'm getting 0. So is it a function of y? I said it wrong. With respect to y. I'm differentiating this with respect to y, but apparently it's 0 because there's nothing here, right? I matched up the 1. I matched up the 3xy squared. The g prime is the derivative of g with respect to y is 0, means that it's not a function of y, it's just a number. It's some constant. This is actually a real number. So this is my potential function, x y cubed plus x plus some number.
Isn't the one supposed to be just as theorem?
What I do? Where?
Are you differentiating with respect to y?
Right, I'm differentiating this with respect to y, so 3y squared,
So
and this with respect to y.
should be
Oh, this is still x, I'm sorry. Wait. Hey. Ooh, that's troublesome. Ain't it? Anything like this? That's still there. That's weird. Hang on. You're right. So I'm differentiating this with little f with respect to y. First part with respect to y, you get the 3y squared times x, right? This with respect to y is, that's actually 0. Oh, that's what I did. I'm sorry. Whoopsie, bad teacher. All right, well, I got an eraser. So x is a constant, differentiated with respect to y is just 0. Okay, so let's, you know what, let's just get rid of this. Okay, now, okay, that makes it easier. Okay, good. I like it. I like you. You're good. You're good to have around. Okay, so we got the 3xy squared matches this, and the 1 matches this. So, there you go. So what's g? Is it a function of y? In fact, it is y. Do you see it? If g prime is 1, when you differentiate with respect to y, then integrate with respect to y, the 1, and you get y plus a constant, now a real constant. So what's your potential function? xy cubed plus x plus, what did we just get for this? Y plus some number, some real number, whatever it is. Okay? So f, okay, so that's f. So f turns out to be xy cubed plus x plus y plus a constant, whatever it is, some real number. I don't know what it is. Now let's check it. Is the first partial of this f with respect to x the y cubed plus 1? Let's just check our work. Take the first partial of this with respect to y, do you get y cubed plus 1? You do, right? Okay. Take the first partial of this with respect to x, do you get 3xy squared plus 1? Because yours get to have around. The derivative of this with respect to x, with respect to y, this is n, f sub y, is 3y squared times x, right? Plus, with respect to y, that's 0, plus with respect to y, that's 1, and that's a constant, so go, yeah, good, perfect, okay. So now what does the fundamental theorem of line integrals say? To get the work done along that curve, from 0, 0 to 2, 0, what do? Plug in 2, 0, plug in 0, 0, subtract, do you get 2? Didn't we get 2? Yeah. Which part? From here to here? All right, the derivative, okay, so this is supposed to be the first partial with respect to x. So to get f from it, we'll integrate with respect to x. But I don't know what this is because I'm integrating with respect to x, so this could be some function of 1. Right? Because again, how do you check this step? So if you differentiate this with respect to x, do you get that holding the y's constant?
Is that G or Y?
That's a g, yeah.
Where did G come from?
I made it up. I called it g. I'm giving it a name. I don't know what it is, so I'm just calling it something.
So why would you put it
Because it's got to be something that's got to be there. Look, if you differentiate this with respect to x, first partial with respect to x, do you get that? The derivative of this with respect to x is y cubed. The derivative of this with respect to x is 1. The derivative of this with respect to x is 0 because it's a function in x. I don't know what it is. It could be like y cubed or something. I don't know what it is. Right? Because when you integrate, you're off by at most by a constant. But in this case, the y's are constant because I'm differentiating with the partial respect to x.
So have you been doing partial wrong all along?
Yeah, but I'm saying I'm undoing the partial. This is just like next to solving partial differential equation, because this is a differential equation for f as a first partial in x, and this is differential equation of f as a first partial of y. So you're actually solving for f. You're solving a system of two partial differential equations. Sneaky. I'll tell you. So the antiderivative with respect to x holding y constant is this, which matches, which doesn't match anything. And then the first partial with respect to y is this, and this matches this. Look at it. This is supposed to be the first partial with respect to y, the 3xy squared and the 1. So if 1 is the derivative of the g that I don't know, then g had to be y. Right? Because the derivative of y with respect to y is 1. That's how I get the 1. So there is something here. There's a y here. And again, when you integrate, there's still a constant of integration, but now it's down to a real number. You got rid of all the x's and y's. So if you plug in the point 2, 0, right? 2 times 0 squared plus 2 plus 0. Now, remember what happens with the plus c when you do a definite integral. What happens? You plug in one endpoint, you plug in the other endpoint, you subtract, but they both have a plus c, so the c's cancel, right? So it doesn't matter. The plus c doesn't really matter. Okay. So plug in the endpoint. Remember, it was a semicircle above the x-axis centered at the point 1, 0, going from 0, 0 to 2, 0, right? So plug in 2, 0. What do you got? 0. Plug in 2, 0 here. X is 2, y is 0. You got 2. Okay. That's at the endpoint, minus the starting point. Plug in 0, 0. 0. Plug in 0, 0. So you got 2 plus c if you want. You can drop this. You got 2 plus c minus 0 plus c. The c's cancel. You got 2. Isn't that what we got the hard way? We did it the hard way. So what does that mean? There's a consequence. There's a lemma. It doesn't matter which way you go. Did it matter that you went along a circle? Could you have gone maybe like straight across, just a straight line segment from 0, 0 to 2, 0? And make the parameterization real easy? What would it be? It would be x of t is t and y of t is 0. If you did it parametrically, where x of t was t and y of t was 0, and t goes from 0 to 2, parametrically, you'd get the exact same result. You'd get the 2 Newton meters. This thing goes to sleep every hour or something? Okay? So that's a fundamental theorem of line integrals. It's sort of like the fundamental theorem in elementary calculus. We're only doing f of b minus f of a. Now you're doing the potential f at the end point minus the potential f at the beginning point. And the path that you choose doesn't matter. The answer is path independent. The work done is path independent if the vector field is conservative. Conclusion. I'm done. Okay? All right, ready to go over the pretest? Any questions up to here? That's all you need to know for the pretest. Stuff from the next chapter, I think it's chapter 18, the reading that was listed there, that's really for next week. Don't worry about that. Yeah.
What's a non-conservative vector?
A non-conservative vector field, the path matters. If you go from point what did I call it? P1 to point P0 to P1, and you go in this direction, you get an answer. You go in this direction, you get a different answer. You go in this direction, you get a different answer because the force field is not conservative. But most force fields that you're interested in electromechanics, in electromagnetism, in electrical engineering, like magnetic field, no, not magnetic fields, like electrical fields, in physics, mechanics, gravitational fields. A lot of these things in the real world are conservative vector fields. So all the stuff we're talking about here applies to the real world, and you can use it in physics if you go on to, advanced physics and engineering and stuff like that. So there. But we can handle non-conservative fields by parameterizing the path. We can still do that if we want to, if we need to, right? Okay, so that's all for recording. So goodbye, YouTube. I hope that was